welcome back to the third lecture. Thank you for coming. So let me just start with a brief recap of what we did this morning. So where did we end up on? We derive, or we at least stated, and I claim that the proof is kind of easy, so that's why I was not doing the board. And if you are interested, you can look at the notes for the exercise, like the guided exercise to prove that. So what we established was a large deviation principle for the Boltzmann-Gibbs distribution. So we started, let's try to go back a little bit and think in a high level what we're doing. So we introduced this probability distribution over the hypercube. So the total number of configurations is like exponential in the dimension, so 2 to the power d. So we introduced this measure. So this measure is a very high dimensional measure. But what we end up seeing is that actually when the dimension is large, precisely in this limit, we can prove a large deviation principle where this measure effectively factorizes conditionally on the mean magnetization of the system. And that's quite remarkable because it means that conditionally on the magnetization, which can be determined by a self-consistent equation, the measure is basically trivial to sample from. So that's quite remarkable, and that's what we call like a mean field model. So that's the typical phenomenology that you're going to face in mean field models. Okay, so the large deviation principle that we stated can be stated either for what we call the free energy density or for the Gibbs-Boltzmann distribution. So here I'm stating for the free energy density. And essentially we ended up with this study of this self-consistent equation that is the equation that determines what is the typical magnetization of the system. So the typical magnetization of the system is the solution of this equation that actually maximizes this large deviation rate, which I called phi. So we started studying this problem in the setup where we had no external field, so H was equals to 0, and we saw that there was a phase transition, and this was a continuous phase transition. In which sense? That if you look at this potential as a function of m, we saw that below a certain beta or above a certain temperature, the system has only one minima, and this minima is the global minima, which is m star equals to 0, meaning that we are in a paramagnetic state. So the mean magnetization is actually 0 with high probability, according to our large deviation principle. So there is a temperature that if the temperature is above that, essentially, if you sample from the Gibbs-Boltzmann distribution and you compute the magnetization with high probability, it's going to be equals to 0. Then we saw that there was a critical temperature such that below this critical temperature or above this beta C, the system develops two global minima which have the same energy, while the 0 global minima, that was the global minima before, becomes a local maxima of the potential. So this transition was continuous. So in this phase, so below this certain temperature, actually, if you sample from the Boltzmann-Gibbs distribution, with high probability, you are essentially in a mixed state between these two minima. But we also saw that in practice, we know that actually we are not going to observe this mixture, right? Like what is going to observe is that in real life, in real nature, where D is finite, what happens is that when you prepare your system, you prepare it in a state, and when you cool it down, you're going to converge to only one of these two minima, and then the system is going to get trapped there because this barrier to jump from one minima to the other, like to mix, actually is exponential. Like the time that it takes is exponential on the size of the barrier, and the barrier is linear in the dimension of the system. So it takes exponential time in D to be able to jump from one side to the other. So if you would actually prepare, let's say, your favorite sampling algorithm on the hypercube, like some kind of Markov chain Monte Carlo or Glauber dynamics, like some kind of local dynamics, and you start at 0 magnetization, let's say a random configuration, of course, the mean is going to be 0, but you would start with a random fluctuation 1 over square root of D, either positive or negative, and then eventually your system at some time is going to converge to one of these two minima, meaning that the Boltzmann-Gibbs distribution is going to have with high probability either M star or minus M star magnetization, where the one that you end up on is the one that is closest to where you initialize. So if your statistical fluctuation in the beginning is towards positive magnetization, you just converge to positive magnetization. If it is negative, to the negative one. And we ended up in this comment, which I think I rushed a little bit, on how can I interpret this in a computational way. So let me just repeat what I just said in a little bit more, let's say, mathematical way. And the relationship between this kind of picture and what is the impact of this type of phenomenology to algorithms. So let's say that I have, let's say, an algorithm that I start with some configuration at 0, and usually as 0, so my goal is to find the ground state. So my goal is to find the configuration of minimal energy. And we know that the configuration of minimal energy corresponds to one of these local minima in minus phi. So I don't know what is the configuration of minimal energy, otherwise I would just use it, right? So usually you don't have any information on what it is, so what you do is that you initialize your algorithm randomly, which means that you sample configuration from uniformly from the hypercube. And then you run some algorithm of your choice. Typically, we use like iterative algorithms, so an algorithm that takes the configuration at time t and update it. I would like to say something like gradient descent. Of course, like gradient descent doesn't make any sense because we are in a discrete space. But think about like the equivalent of gradient descent. We are making local moves, so we are changing just a small number of spins at every step. And our goal is an algorithm that goes down in energy. So think about an algorithm that makes local moves and on average is going down in h. So it's kind of doing like gradient of h move. So I'm not going to be explicit, but you can write down such an algorithm. So one example is Glauber dynamics, for those of you that know. You can also write a Metropolis algorithm for that. Okay, so in this case, if you go down in energy and you look at what this type of algorithm means in terms of the magnetization, so you can equivalently write something like for the average magnetization. So remember the average magnetization, let me remind you what this notation means. That's actually literally the average over the spins. So you could use your algorithm and see what this means for the average magnetization. You get something like another function g. And so when d is large, like doing a descent, like doing a local algorithm that minimizes the energy is going to be like some kind of a gradient descent, some kind of a descent algorithm, which is also local on the potential phi. So moving locally here implies that you're moving locally in this energy landscape, but this free energy landscape, which corresponds to the landscape of the summary statistics. And the summary statistics for us here is this average magnetization. So you would be doing like some kind of gradient descent in this potential here, if you're doing gradient descent on the energy. And so what this phase transition means for this algorithm is that initially, at your initial state, you're going to be close to 0, right? Because the average magnetization of the uniform configuration is around 0 with a fluctuation of order 1 over square root of d. And then you would go down in energy. So if you are in the paramagnetic state, that's easy. You are close to the solution and you just mix very easily. Now, above the transition, what happens is that you have these two minima, and then, as I was saying before, you would just converge to the one which is closest to the initialization. And actually, the time to mix, actually, and to see both states would be exponential in the dimension of the system, so you take a lot of time. Now, but what's interesting to me is that what happens around the transition. So we saw that since this is a continuous transition, the minima around the transition is very flat, which means that actually, if you are at beta plus, so if you are around beta that you already developed the local minima, but you're very close to it, you have like this very, very, very flat flat space around zero. And so to escape that, you need to make many moves to actually find the minima. But now remember that moving order 1 in this potential means moving order D in the initial configuration. And one way of seeing this is that at initialization, in terms of the space of configurations, there are D directions that you can flip your spins, and all of them are flat. And you can think about the minima as being like, let's say, like in a golf course, like it's just a hole in this D-dimensional space. There are just too many directions, all of them is flat, and the time that you're gonna take actually to escape is gonna be very large in D. And that's what we call critical slowing down. And one very concrete way of seeing critical slowing down is that you could just essentially plot the time of convergence against like beta, and then around beta equals to 1, you're going to see that you have a curve that essentially looks like this. And by the way, in machine learning, there has been, that's just a comment for those of you who know, there has been a lot of work recently around like single index models and gradient descent for single index models. So all of this started with work of Gerard Benaruz in 2019 with Reza Gennari and Okosh Yagana. And essentially they were showing that if you are learning like one hidden unit with a nonlinearity, you had a phenomenology that is very similar to that. And they call this escaping mediocrity. So that's exactly the same phenomenology as we are observing here. Okay. That's a comment. If you know what I'm speaking about, that's good. If you don't, just ignore me. Okay, it's essentially entropy, an entropy factor. Yeah.
So you said that because we start uniform, we're starting very close to zero.
Yeah.
How many you just want to go to zero?
In this case? In the second case. Yeah, so if you are just below beta C, so beta C, beta equals to beta C minus, then it is still, let's say, okay, here is still easy, I would say, right? The problem is like when you are in beta C plus. But anyway, like the fact that this is very flat, the time you take to actually explore this very flat minima is still going to be very large. But it's true that strictly speaking, like mathematically speaking, at beta C minus, there is only one minima, and 0 is the fixed point, which has the minimal free energy potential. Okay, so that was everything that I wanted to tell you about the zero field. Let's now take a look at the finite H, which without laws of generality, let me just take H larger than 0. Everything that I say is going to be true for H less than 0. Just need to flip the signs. So now there is no Z2 symmetry. Actually, you can see H as a bias in this Boltzmann-Gibbs measure, which bias a sample of the measure to have magnetization which aligns with this field. And in particular, m equals to 0 is not fixed point of m equals to tan h beta m plus h. Okay. Again, let's take a look at the limits so that this simplifies our life, and then we can see what happens in between. So at high temperature, so beta going to 0 but plus, you can check that the limit as beta goes to 0 plus of the potential is equals to h. So At very, very high temperatures, you always have a magnetization which is equals to H. And as you lower the temperature, as beta goes above a certain critical temperature, you have two possible behaviors. So now, if you look at this function and you plot it, you essentially have one behavior if you have a small field, or H less than certain H that depends on beta. This is HSP, I'm going to explain why. But essentially, if you look at phi, or minus phi, essentially what you have now is something like, let me try to draw this precisely. Something like that, where I have the single global minima, m star. I have one critical point here, which is not zero, because again, zero is not a fixed point of the self-consistent equation, and I have a local minima here. But there is a gap. Very importantly, there is a gap here. There is a delta phi. Where I remind that m star is equals to the argmax of phi. So the one that actually corresponds to the equilibrium magnetization, so the magnetization of a typical configuration from the Boltzmann-Gibbs distribution, is the one that actually maximizes the large deviation potential. So this is interesting because it means that, actually, again, this barrier is going to be an order 1 barrier in the space of phi, which means there is an order D barrier in the space of the configurations, which means to jump this barrier, you need exponential time due to Arrhenius' law that we discussed last time. So this means that if your system is in one of the minima, you will never escape this minima. So if, in particular, the system is in the wrong minima, so like the local minima, you stay there. You will never mix. Actually, you take exponential time to mix, and actually to see the true global minima, the true ground state of the problem. So let me write this. Delta phi, which is phi of beta h of m local minus phi of beta h of m star. So this is a O1 quantity. But because we have our large deviation principle, that S bar D equals to m local, the probability of this thing is going to be e to the beta delta phi. And so a local algorithm will take a time which is proportional to E of D times delta phi to be able to jump if you are trapped here to here. And that's exactly the same phenomenology we saw in the first day with the beer, right? This beer that, it was a super cooled beer, and then it was in a liquid state, and then you tap it, and then it starts freezing because it essentially jumps the minima. So in the case of the beer, we were very close to the transition where this potential difference was very, very small, and so just a little bit of thermal fluctuation was enough to make you jump. But let's say if you have like a very big gap, you never make this jump with a small fluctuation. But the phenomena is the same, right? It's like the fact that you have like two minima and the ground state of the system is the one with minimal energy, and then the system wants to go there, but it is trapped in another minima. Yeah.
So you want
Yeah.
heat in between matter, that should also matter, right? Like we
Um,
go above it.
Yes, that's true. That's true. So you actually what is going to matter for the time scale is the height of the peak. Here I was just writing like what is the probability actually for you to let's say that you are in this state and you want to say what is the probability of an event that takes me from there to there. So that probability is exponentially small in the difference because of the large deviation principle. But it's true that dynamically, if you're actually running Markov chain Monte Carlo, what is going to matter is rather, yeah, that's let me define the second one, which is delta E tilde. And it's true that maybe here I should put a tilde. Oh, not here, sorry, here. So it's both rare in terms of the equilibrium state and rare, like, and takes a lot of time dynamically. Thanks for that. And now, what is going to be the computational takeaway in this case? And that's going to be the key notion that I want to introduce, computational, that I want to introduce in this model. Which is what this type of phenomenology implies for a local algorithm, is that metastability can trap local algorithms. Meaning that, again, let me repeat this again because it's the central point, is that if you start here and for some reason, for some small like statistical fluctuation, you are more to the left than to the right, you're going to converge here. And you will never be able to go there unless you make a non-local move or that you wait very long time. So while here is a bit of it's a bit not very natural in terms of computation, because first, why would you initialize here? Okay, you would actually initialize at 0 because you initialize at the random configuration. So actually you always finish here if you initialize at very, very high temperature. But as we're gonna see later for linear estimation, actually this picture is all shifted to the right. So actually when you initialize at 0, you always fall, your algorithm is always gonna fall first into the metastable state. And this is going to imply that there is some computational gap between the best algorithm that we know within first order methods and the optimal Bayesian estimator. And that's what we're going to see next. But the picture is exactly the same. So, okay. And then let me just say, for completeness, although this is very much the uninteresting part, is that for large field, for large H, so H above this HSP beta. By the way, these quantities you can compute, right? I mean, I'm not going to spend time in this because that's not the point here. The intuition is more important, is that now things become convex. And then you just have one global minima, which is going to be positive. So if the field is large enough, your measure is very much biased towards configurations that have magnetization aligned with the field, and there is nothing you can do. Like there's just one minima. Like a typical configuration will align with the field if the field is large enough. Yeah.
So what exactly does H mean?
So that's something we were discussing last time. So this H is what we call in physics an external field. So very concretely, if you are in a lab, you can put your magnet in a magnetic field. So what would happen in real life is that if you want to prepare a magnet that you can stick to your fridge, you'd get a metal that is susceptible to magnetism, and you would put in a very strong field. What is going to happen? The magnet is going to magnetize in the direction of the field because of this. because if the field that you put is large enough, you go in this direction. And then you take it out. Since this is stable, even if you now take out of the field or you cool it down, you stay there, because this is a stable state in equilibrium. Now I give to you, and this is a magnet you can put in your fridge. Then you can heat it up if you want. You put this into the stove and you heat it up. What is going to happen is that at very high temperatures, you're going to see there's going to be a phase transition, and what is going to happen is that you're going to lose magnetism, because 0 is going to be the solution of this problem. So you're going to lose your magnetism. And then we were discussing, and a lot of people were curious about that. It's kind of funny, I mean, that people were so curious about the physics of this thing, but what is going to happen now that you cool down again? Like, your system now is in the paramagnetic state. Your system is at 0. Now that you cool down, what happens when you cool down? Well, this happens when you cool down. So what is going to happen is that as you cool down, if you cool down slowly, different parts of the system might transition to different minima, let's say, to different sides of this potential, due to small statistical fluctuations at local pieces of the metal. And on average, you might get a total magnetization that is, let's say, positive or negative, but because of this nucleation that we call, the average magnetization, if you start from the paramagnetic state, is going to be 0. So you won't retrieve your magnet if you just cool down, put in the fridge. In order to actually remagnetize your metal, you need to go to the lab, and you need to put in a strong magnetic field, and then it would go back up or down, and then you can repeat this. But okay, that's a bit out of the scope of what I'm saying, because I'm mostly interested in the computational aspect of this thing. Okay, so now let me just make a plot, which is the plot of, maybe a little bit to the right, which is the plot of what happens with the magnetization as a function of h. And essentially, what you're going to get is something like that. It's a bit of a tricky plot. Maybe the blue one. So if you are below the critical temperature, so beta above beta C, that's the behavior of the magnetization as a function of h, is that you have this type of behavior where there is a critical h, such that above this critical h, you just jump. And the reason is that exactly because there is this 2 minima. So whenever you have this kind of metastability in the free energy potential, what you get is this type of discontinuous transition on your summary statistics, and this discontinuous transition is always going to be associated to this notion of metastability. So there is a one-to-one correspondence between these metastable states and first order phase transitions, if you want. But I mean, discontinuous transitions, which are, remember, this is very different from what we had got into the zero field case, in which the magnetization had a continuous transition. So that was the plot that we had before, remember? And this was the beta C. And then actually you can make this plot now in the space of beta and h, and this is going to give a surface, and you have the jump in this surface, like this surface, this is actually what is called catastrophe theory, and you can look at these bifurcations on the topology of this surface in this three-dimensional space. There's a whole theory in mathematics about that, although that's not the point of the lectures, but if you are interested, you can take a look at catastrophe theory. Okay, so my main message here is that I wanted to tell you is about the impact of this type this type of gap that you have in the landscape of the summary statistics in terms of like local algorithms and how they can get trapped in local minima if you have this type of landscape. Okay, any questions about that? Yeah? Yeah. Yeah, so okay, let's try to see this in two pictures. There is the physics picture and there is the computational picture. So in the physics picture is what I tried to convey in the first lecture, is that how do you prepare materials? Like how do you actually design this type of materials? Like typically what you do is that you heat them up. So let's say you take sand, you heat the sand and the sand become a liquid, right? So you start in a very high temperature state, which typically is a disordered state. Like, you know, you have a liquid, all molecules are all over, and then you start cooling it down. And as you cool it down, the system is gonna internally try to go to an equilibrium state, so it's gonna try to thermalize. And depending on the way you cool down, the picture is that you end up in one of these low energy states as you lower the temperature. So that's the picture that I tried to convey in the first lecture, and that's the relationship between, like, you know, the physical dynamics of cooling down and the equilibrium configuration, which is the large deviation principle for this potential. Now, in terms of local algorithms, there is no temperature, right? Like what there is in local, okay, there is a temperature if you're trying to sampling, but you can typically what you're doing is that you start at a random configuration of your problem, you initialize your weights randomly, uniform distribution, Gaussian distribution, whatever. And then you run a local algorithm, GD, SGD, AMP. You choose your algorithm, but like something that is typically local, and typically this algorithm is trying to minimize some objective function. So in GD, you are minimizing some loss function. So if you could derive a large deviation principle for this loss function in terms of some macroscopic statistics of the weights of your neural network, and you could have a picture like that, where M is some aggregate of the weights of a neural network. Let's say you take the average weight, or you take the correlation of the weights with some target function that you're trying to fit. If you could derive a picture like that, this picture would imply that for your neural network, if there is too low, so there's a local minima and global minima, if you start your gradient descent at a random configuration, and you end up in a local minima, your algorithm is never going to jump the barrier. So it would imply that there is this computational gap for local algorithms. So that's the connection between, like, say, computation and this kind of stuff. But of course, it's not clear at all how you derive, first, what is the order parameter for the neural network? Second, once you identify the order parameter, can you actually prove a large deviation principle for some potential on this order parameter? And then once you have that, you can have this nice picture. But it's not obvious at all how to do this in like a two-layer neural network. And that's where we're going to go next. We're going to look at a concrete machine learning problem where this picture can be derived. But the reason why I'm doing this is because here I can completely solve the model and I can plot everything and we can discuss this in a very concrete setting. The example that I'm going to consider next is going to be much more opaque. Like even this space is not just one order parameter, it's going to be more than one. So you have to draw surfaces and things like that. Yeah?
I'm a bit confused between these pictures and the pictures you had on the first day.
Yeah.
So on the first day you had a picture that looked like that, but then you said think of it as water, and then as you decrease the temperature, you're coming down. But in this story, if I start at high temperature and start decreasing temperature, I should start with a picture corresponding to that, which is like just a convex function.
Yeah.
And then it starts, the landscape itself starts changing, right?
Yeah. So that's a very good question, because so the way we think about this, so this is more like a way of thinking about this landscape, right? Because what I'm drawing here is the potential for the large deviation function. So this potential is about the equilibrium of the system, and this potential depends on beta. So the potential is changing with beta, and it's becoming like a convex and then developing minima and so on. So actually, I was tricking you in the first day when I was give you this potential, because this potential is not independent of beta. This potential depends on beta. But typically, one way of thinking about it is like consider the potential at beta, which is beta equals to infinity, so low temperatures. So here we are at low temperatures. That's the hard part, right? So you start with the hard part, and then you know that because at high temperatures you have the uniform distribution, for example, is going to be convex. So that's where you put your water. So if you put your water level high enough, whatever the minima are, you're going to see something which is convex. And then you can see like lower temperature, lowering the temperature is going down. And then when you have zero like water, you are at the beta equals to infinity point. But it's just a way of thinking, right? It's not exact. But whenever you see these plots, like the diamond plot that I show you, essentially that's what they are doing on the back. But that's a great question, because yeah, there is a bit of a leap here between the two things, the things we are doing and the thing that I showed in the first day. But I'm trying to give you like a little bit of the way that physicists think about this problem. Yeah.
So basically, down my magnet very fast. It's like given it a lot of it's like I would be able to jump to this like local maxima because I immediately gave a lot of sort of like energy.
No, I would say the opposite actually. Like, so let's think about this at zero temperature. This is the large deviation potential at low temperatures. So if you start at a random state, you start something like around zero, let's say here. If you cool very quickly, like, you know, instantaneously cooling, what is going to happen is that you essentially find yourself in this landscape. And then your algorithm is going to go down here. So, however, when you do simulated annealing, you don't cool very quickly. And that's the important part. When you do simulated annealing, you start at very high temperatures and you find the temperature scheduling in such a way that you want to end up here, right? So all the magic is in the way that you cool. And the way that you cool, if you do it well, you're going to end up here. So you're going to go down, and then, you know, around the transition, you're going to be at this basin, and you hope that your algorithm doesn't go here. But that's also like, yeah, all the magic is in the cooling. And also in real life, right? Like all these artisans in Venice that learn how to make amazing glasses, they cool it in a very fancy way. You know, it's not just like putting in the fridge and wait, right? Like they are spinning this thing and so on. Or when you temper chocolate, you're also like, you know, mixing your chocolate in a very particular way so you get the right crystal that melts at the right temperature in your mouth, but is solid at your hands. So the cooling is the magic. That's the same thing for gradient descent, is the learning rate schedule. That's the magic, right? Large learning rates, small learning rates, like the way you change it, that's the magic. And essentially, this gives you a way of thinking, like the relationship between the large deviation principle and the algorithm would give you a way. If you knew this potential, you would find a way of finding the optimal cooling. Yeah.
I think there's a typo for high temperature.
Yeah. So the potential should be, so strictly at zero, you have, you are at the uniform distribution, but for any small, like for any small beta that you have, wait, oh, sorry, that should be, I think, yeah. That should be the entropy, and I guess that I wanted to say, wait, I wanted to say that, yeah, sorry, yeah, you're right. What I wanted to say that the limit beta going to 0 of m star is equals to h. So m star, which is a function of beta and h, is equals to h. And my claim is that if you do things carefully, that point here is h. Or that's the local maximum at low temperatures. But all of these things you can just compute because it's just a quadratic function, quadratic plus a logarithm. So you can compute all of these things if you work hard. By the way, this value here, which I call HSP, is called the spinodal. And that's essentially the point. So if you look at this landscape as a function of h, as you vary h, I claim that at some point you go from being like convex to having like two minima, and this happens discontinuously. As soon as you cross this point, one minima appears discontinuously. And whenever this happens, we call like this the spinodal point. So that's something you can also compute, but okay, it's not the main purpose here. I think in the notes I compute all these things explicitly if you're interested. Okay, let's move on because otherwise we won't get to the interesting part of the tutorial. So now let's move to a second part of the tutorial, which is the toolbox. So here we are going to move away from statistical physics, or at least a bit, and we are going to be considering learning and inference problems which are a bit closer to what most people are used. So let's consider two problems, which at first sight they might look quite unrelated, but I claim that we're going to be able to treat both of them together. So the first problem is the problem of Bayesian inference. Or if you want, inverse problems. So these are problems that take the following form. So you observe some data from some distribution. Typically, this distribution is a parametric distribution. And you observe, let's say, n samples from this distribution. Let's assume they are IID, always keeping in mind what Matos was telling us in the first lecture that, you know, real life is more complicated than that, but that's the typical setup we study. And there is a true parameter theta star that has been sampled from a distribution P star. So you observe these samples, so observe the data Zi. Your goal is estimate to find an estimator theta hat, which is a function of the data, which is close to theta star. So that's a very natural problem, right? It's everywhere. So for example, you're doing a Zoom call with someone. You have your voice. Your voice is a signal. You're sending your voice, you're encoding your voice in the computer. The voice is going to a satellite and going somewhere and arriving at the other side of the Atlantic, like to someone in Europe, and is being decoded, and they can hear exactly your voice. So that's essentially like, this can be put in this framework. You are like sending something, encoding something into a likelihood, then decoding, and then the goal is like to estimate the signal being the voice from the observation, which is like this encoded signal that is being transmitted. So many problems that you are interested in science and so on, like can be written in this way. It's fairly generic. And the relevant questions that you would like to answer so the quick questions is, for instance, how many samples do I need to be able to estimate theta star precisely? So what does it mean to estimate theta star precisely? Do I want to estimate theta star exactly? Do I want to recover theta star exactly? Do I want just to have some correlation with theta star? And then more importantly than these two things, and that comes to something that Cynthia has motivated in her lecture, is that, you know, what is relevant is not actually estimating theta star. What is relevant is actually estimating theta star in an efficient way. Because if I can estimate theta star in exponential time in the dimension of theta star, means that essentially that is useless, right? So in the end of the day, I want a procedure which is efficient to estimate theta star. So like questions. This is almost gone. Oh, nice. So questions. So question 1, how large you need n to be? Question number 2, efficiency algorithm. So an algorithm meaning a procedure that takes, you know, your data and gives you an estimator of theta star. So an algorithm that runs, let's say, in polynomial time in the dimension of theta star. So another question which is very important that also Cynthia has motivated in her lecture is that if I have some information about P star, like if I have some information about my signal, for example, I know it's sparse, I want to use this information. So how can I develop algorithms which are adapted to the structure that I know? So this might seem crazy that you know some information about your signal, but you know, in many situations that's the case. So in the Zoom example that I gave to you, some engineer actually built this antenna, some engineer, software engineer built the code to encode and decode. So the process of transmission is known sometimes. And then how can I leverage the knowledge of the prior to actually produce more efficient estimators? So leverage P star or knowledge of P star. How do we do this? Okay, so here there is one case which is the best case scenario. So that's, you know, ideal world, but okay, it's going to provide us, let's say, a bound at least, is when the likelihood, so let me denote in this way, P of, okay, let me be consistent with the notation. I just realized that I did differently from my notes, but I'll try to stick to it. If these two guys are known, so if the likelihood where I sample the data and the prior where I sample my signal, they are known to the statistician, then, you know, at least in theory, the problem is actually easy because, again, like that's something that is closely related to something that Cynthia did in her lectures. The maximum, so the minimum mean square error, which is like the minimum over all measurable functions of the data on average over theta star and over D of, let's say, all possible estimators, which are functions of D minus the signal. So in mean square error, the minimum is actually achieved by the posterior mean. So I have an explicit construction of the best estimator in L2 norm. And actually, give me any other norm you know, I can construct the best estimator in this norm from the posterior as well. So that's one example. Average over theta given D minus theta star. So this is exactly the result that that Cynthia proved, but she was proving this in terms of mean square error for y, and here is the same result for mean square error on theta. But the proof is exactly the same. You exactly do the same steps that about 1 hour ago you did. So let me just be explicit where P of theta given D, so the distribution that I take the expectation in respect with is proportional to I from 1 to n of the likelihood of P of theta Zi P star of theta. So that's the posterior distribution. Note that I can only compute this if I know the likelihood and the prior. If I don't know the likelihood and the prior, you cannot compute this. But if you know it, that's the best thing you can do. Is just like try to construct this distribution, sample from it, compute the mean, and the mean is going to be the optimal estimator in mean square error. Now there is a catch here, right? What is the catch? Is that sampling from this high dimensional distribution, it's hard in general. It can take exponential time in the dimension of theta. So in the worst case, this is actually hard to solve this problem explicitly this way. So, you know, it's out of question to actually sample this thing in practice. That's not a valid algorithm. That's not an efficient algorithm to solve the problem, not even when you know the posterior distribution. Right. So I just want to say one thing, which is something that we don't see very often in statistics book, but it's going to be important for us. So I just want to mention this result. It's called the Nishimori identity. And we will need it later. So that's a good place to introduce it. Is that in the base optimal setting, and base optimal setting is what I mean the best case scenario. So that's what I call base optimal. When we actually have information about the likelihood and the prior. So in the base optimal scenario, take any two samples of the posterior. So the expectation over any two samples of the posterior, theta 1 hat, theta 2 hat from P of theta given D, take any function of these samples because of base optimality. I claim that this is equal to the expected value of theta star from the prior and one sample from the posterior. So did anybody, I mean, apart from the speakers, saw this before? Because this is something that is not very often taught in statistics, but it's something that it's actually quite easy to see if you just write down the definition, and is a direct consequence of base optimality. Is that if you take any function of samples of the posterior, you can change for functions of the prior. You can change one of them for the functions of the prior, and then compute the expectation with respect to that. And you can just prove this by writing down the definition and use the fact that actually the posterior is the base optimal posterior, is the one that has the right prior and likelihood. And by just conditioning, you can see that this is true. So I'm going to leave this small probability exercise, but that's going to be very useful for what we're going to do next. So let me just give you a few examples of Bayesian inference problems that we like. So example. So the first example, of course, our favorite example, is linear estimation. So in linear estimation, my data is just pairs of x and y. and y given x is just linear up to some noise. And theta star can be, again, a generic P of theta star. So that's a very concrete example of what I said before, is that, okay, you observe y depends on x for the projection on theta star plus some noise, and the goal is that you observe n observations of y, and your goal is to estimate x. And in particular, when theta star is k sparse, so when this is a sparse vector, meaning that this distribution is essentially saying that this guy here has k zeros and d minus k non-zero elements, then we call this the compressive sensing problem, also known as compressive sensing. And this is something, I guess, that most of you have heard about. All right, so it's one example of a inverse problem. So another one which is closely related, also when zi is equals to xi and yi, but now my yi is the absolute value of theta star xi plus noise. So there are two versions of this problem. The absolute value can be here or can be here. Doesn't matter, like both are valid problems. This version is more common, and this problem is called the phase retrieval problem. So this problem, for example, is very common when you're doing physics or you're doing biology. You are in the lab, and then you throw some light in some material, and then the light hits the material, comes back, and you measure like what came back, and then you want to infer some property of the material by looking at the light that came back. So this optical process typically is a linear process, so that's nice. However, your measurement usually can only capture the amplitude of the signal, not the phase. So you lost some information that you want to try to recover. So essentially, you observe just the amplitude, and the goal is to recover the phase. So in the real case, that's just the sign of this scalar product. But if these were complex variables, this could be a full phase of a signal. So that's, for instance, something that is very concretely done when you do crystallography, for example, X-ray crystallography. So it's a very important problem, and solving this thing efficiently is actually like an important business, like for a lot of actual labs. And there are many papers about that, algorithms to solve this thing efficiently. Finally, I just want to introduce a more general problem that covers these two examples. So more generally, you can think that your y is sampled from some likelihood, P, that only depends on the projection of x in some direction, and this theta star is a sample from some P of theta star. So in this case, I have a genetic likelihood, and this likelihood could be in particular the phase retrieval. This likelihood could be the linear case, could be something else, power 3, 4, could be the tan H, the ReLU, whatever you want. So this problem here is called, so this one is called generalized linear estimation. Okay, any questions about Bayesian inference and inverse problems? So this is a particular kind of example you're going to be interested in studying in the following. So, and in particular, you're going to be very interested in the Bayes optimal setting, not because we believe that, in real life you have access perfectly information about the process that has generated the data, but because that's the best case scenario. So that's going to be very useful to derive some bounds. Yeah.
So it's like the prior distribution and like theta hat, like the observed distribution.
So theta hat is my estimator. So the estimator is any function of the data that you want. So you observe the data and you do whatever you want with the data, and then you give me an estimation of theta star. The distribution of theta star, I'm going to call it P star. So P star, sometimes you can call it like the prior distribution, but it's not a very good name, because that's actually the distribution where the signal has been drawn from. So it's not the prior of the statistician. Of course, in the base optimal setting, the statistician uses the same prior as the one that has generated the data, because if you don't do it, if you have access, why wouldn't you use it? But in general, you can make this distinction between the prior, which is what you're going to use to estimate, versus the true generative process of the signal, which I'm calling P star. Well, that's what they want you to believe, right? That's in real life you never know, right? I mean, take MNIST, and you want to do Bayesian estimation on MNIST. You want to infer, like, let's say, the classes or something like that. So what is the prior over the parameters of a neural network that actually generated the MNIST? Like, does MNIST has even been generated from a neural network? So in real life, you're never well specified. So you almost never in the base optimal setting. Even though, like, what Bayesian statisticians will tell you is that, if you overparameterize your net, you can express any function. So doing Bayesian inference over overparameterized neural network, you can possibly be expressing the true prior. And so if you do it well, you're going to capture it. But actually, having the right prior is almost never the case. Here, for me, it's not going to be like, it's going to be just a way of deriving bounds on the computational complexity of algorithms, because if I can show that even for the best case scenario, you cannot recover the signal, means that you cannot recover the signal information theoretically. So it's going to be a way of proving information theoretic bounds, the base optimal setting. But in practice, you are never in the base optimal setting. Maybe someone disagrees. Maybe some Bayesian statistics in the room want to has strong opinions on that. But yeah. Right. That's a good question. So in these examples, I didn't mention anything about the distribution of X. Soon I will make some assumptions on the distribution of X, but this depends on the kind of literature you're looking at. For example, in the compressive sensing literature, instead of making assumptions on the distribution of X, they say that X satisfies some geometrical properties, like some RIP, for example. And then you try to prove results for this type of X's. So typically people don't like to make assumptions on the distribution of X, but as Cynthia was motivating the beginning of the afternoon, often if you want to make progress in the high dimensional setting, you need to make assumptions on the distribution of X. Otherwise, in the worst case, you are doomed by the curse of dimensionality. So my claim is that eventually you want to make some assumption. The question then becomes, what are the good assumptions on X, right? Because you don't want to be too simplistic. Otherwise, your result is going to be like uninteresting. But you also don't want to be too vague, because otherwise the curse of dimensionality is going to catch you. So the point, like I claim that one of the main difficulties of doing high dimensional statistics is finding what are the good distributions of X that captures real life and it still allows a mathematical treatment. That's all the kind of juggling of the game. Like you want to be as general as possible, but not too general, because otherwise curse of dimensionality. Sorry? Oh, I'm assuming that is always independent of theta star. But you can make some progress when they are correlated, but then you have to make another assumption on what is the correlation between x and theta star. But for everything that I'm going to say next, they are independent. Okay. So this is one class of examples of problems that we're going to be interested. Let me give you another class of examples that you're going to be interested, and then we can start a little bit of the machinery, so the toolbox, then I promise you. But first, we need to be on the same page on the type of problems that we can analyze. I mean, the second class of problems, I think I won't need a lot of time to introduce because, again, that's something that Cindy spent a lot of time in her lectures, and then also Matus did this in the first lecture, which is just empirical risk minimization. So where did I define? Toolbox 2. Empirical risk minimization. Or also known as ERM. Okay, so empirical risk minimization, essentially what we have, let me go really quickly over that. So like, let's consider one particular case of a supervised learning. So in supervised learning, you have some pairs of data. So this data, we typically like to think that we have vectorized it. Again, you need to be cautious. Real data is not vectorized. Matus, like in the first day, spent a lot of time saying that, a lot of data nowadays comes in sequences. Even when you think about a picture, like, in pixel space, is not a vector. You typically flatten it. Are we losing something doing that? Like when you have like an Excel table, you have 0, 1s, strings, and so on. So one need to be cautious when making these assumptions, but let's go for it anyway. You have some label space. If you're doing classification, this is a discrete set. If you're doing regression, it's a continuous set. And you have n samples, and you're going to assume that the samples are IID. So first, let me define these as my training data. That's my training data, and we're going to assume IID from some joint distribution. So this data has been sampled from this joint distribution. Of course, we don't know the joint distribution, otherwise we wouldn't be doing empirical risk minimization. We would be doing Bayesian estimation. So what do you do is that you choose, so that's one thing. Then you choose a hypothesis class, so a class of functions, trying to be consistent here in notation with Matus. So let's say a class of functions, f of theta, typically is parametric, so depends on some parameter that goes from RD to your predictions, such that theta is in some parameter space. And then what you do is that you want to solve the problem of minimizing the empirical risk, which is the sum from I1 to n of a loss function, which is a measure that you choose. And eventually you also can add an explicit regularization, and then theta you minimize over your parameter space. This guy here is called the empirical risk. So that's the empirical risk. And then it's very natural, like why empirical risk minimization? You're minimizing the empirical risk. And what you're interested is not in the minimizer of the empirical risk because this doesn't guarantee that actually you generalize. So your goal is to study actually the population risk, which is the expectation over the data of the loss function evaluated at the points that were not in the training set. So you want to understand this object where actually once you minimize this, you get the minimum, you plug it here, and you want to understand this object. So that's the population risk. And again, like the questions that you want to answer are exactly the questions that we saw in the first day in the school. So that's like, you know, again, how large n needs to be, because you know that this guy here, by the law of large numbers, when n is large enough, converges to that. So if n is infinity, a priori, you just need to minimize this, and then you solve your problem. So how large n needs to be such that the minimum of this guy has good generalization. But of course, depending on your choice of loss function, this is not convex. And so even if you have access to the population risk, you know, you need to find the minimum. So what is the performance? What is the performance of algorithms? And in particular, you're not interested in any algorithm. You're interested in things that people use in practice. So GD, SGD, Adam. What else did I put here? Oh yeah, how to choose, how to design your architecture, how to choose the hypothesis class you're going to be, the parametric hypothesis class you're going to be minimizing over, 2-layer neural networks, 3-layer transformers. What is the impact of the choice? How does this interact with the data distribution? Because the choice of F usually involves some knowledge of the data distribution. If you're doing sequences, maybe you want to use a transformer. If you're using images, maybe you also use a transformer nowadays, but you know, traditionally we would say a CNN. And what is the impact of the data distribution on all this story? And for me, this is one of the most interesting questions, because as we just said, like a few minutes ago, you know, in the high dimensional limit, the data distribution matters. So in the worst case, solving this problem is not possible. So the answer to these questions, all of these questions will depend on your data distribution. You cannot be ambitious enough to think that you can answer all these questions agnostically of your data distribution. So how does the different class of functions that generate the data, what are the complexity of learning them with certain architectures, with certain algorithms? So this is something that sometimes gets forgotten, but this is very important, especially in the high dimensional limit. Okay, any comments or question about empirical risk minimization? So I didn't spend too much time on that because that's the third time you see this thing in the summer school. So if there are no questions, let me give you some examples of concrete empirical risk minimization problems that, in particular, the ones that we're going to see with the methods that we did, that we're going to introduce. So examples. By the way, I should also comment that what is the difference between empirical risk minimization and Bayesian inference? So in principle, you know, in this case where your data comes in pairs, there might not be like too much difference, like, you know, from a conceptual perspective, but the key conceptual difference between these two things is that typically when you're doing empirical risk minimization, you don't assume anything about any knowledge about the data distribution, right? While when you're doing Bayesian inference, typically in inverse problems, you have some knowledge about the process that, at least some part of the process that generated the data. So for example, in the Zoom example I told you, or like, you know, communication, phase retrieval. So you built the instrument, you built the crystallography thing that you're going to study. So typically you have some information about that. And that makes a lot of difference in the type of algorithms that you're going to design and so on. Okay. So let me give you some examples. The first example, which is again the theory favorite example, is ridge regression. So in ridge regression, the hypothesis class is the class of linear functions. So f of theta of x equals to theta dot x. The loss function is the square loss. The regularization is the L2 norm. And you can solve this problem explicitly. Actually, you can write down an estimator as a function of your data, which is just the solution, because this is a quadratic problem. So that's kind of one of the simple cases. So for any data x and y, you can just write the solution of the ERM. And then typically you assume that yi has been generated itself by a linear function plus some noise. And the reason for that is that this hypothesis class can fit at best a linear function. So anything which is not linear is going to look like noise for the model. So this is almost without loss of generality. And then once you do this, studying the generalization error is just a random matrix theory problem. So you make some assumptions on X, let's say some moments exist, sub-Gaussian, etc. And then you compute the generalization error by using results in random matrix theory. So that's one example. Let's say it's the simplest example where you can actually do theory in the high dimensional limit. So that's one example. Yeah.
So you have lambda.
Oh yeah. Thank you very much. Yeah. So where do I want to put my lambda? I think I want to put my lambda. Let me put here, because I will need everywhere. So yeah, thanks for that. Let me give you another example. So that's also an example that has appeared before, I think yesterday in Mato's lecture, which is logistic regression. So a little bit harder, not as simple as ridge, but it's still simple enough. Again, the hypothesis class can take to be linear functions. Loss function is a logistic loss. So let me take the set of labels to be like just binary classification, where I encode the labels plus or minus 1. So this is going to be important for the loss function. So that's going to be the log 1 plus e to the, I always forget, like, is that a plus or a minus? I always forget. It's a minus. Thanks.
A minus the x.
And a plus here.
Plus.
Yeah, thanks. I always mess up this plus or minus. I know there is one minus and one plus, so I don't know where. Thanks. And then typically you also take this to be the ridge penalty. Can also take something else, but that's one example. And then typically here, like let's say you're going to assume that your labels comes from some probability, let's say the probability of y given some theta star. So that's one example. I'm not saying that that's the only example. And then actually you can parameterize this by some phi of theta star of xi, yi. So that's what is called a probit model, where this is a function, phi is any function that goes from R to 0, 1, because this is a probability. So that's one model. You can also take a Gaussian mixture model with 2 clusters. That's also a good model to study this problem. So just some examples of data distributions that kind of make sense to study with logistic regression. So with ridge, it's quite clear that you want something linear plus noise. So here is a bit more subtle because there are many choices which are give different results and are equally good distributions for binary classification. And finally, let me see in the notes if I talk about the 2-layer case. Oh yeah, no. There is one last thing that I wanted to, one model that I wanted to speak about, like kernel methods. So kernel methods, and here I'm going to be very, very brutal with my definition of kernel methods, but essentially that's going to be, for all practical purposes, that's what they're going to do. So let's say your hypothesis class is an RKHS of some kernel. So the RKHS, usually you think as it's as a subset of L2 of a measure mu. And then you assume that yi is some f star of xi plus some noise with f star some target function in L2 of mu. So mu is some distribution for x, some probability distribution over the covariance. So and then why this model is essentially, I claim, to study this essentially similar to studying ridge regression is because you can consider a basis of L2. So you can expand your f star to be just a sum, a countable sum of coefficients, which I'm going to on purpose call theta star of a basis. So that's a basis of L2. And then once you have this, any predictor in your RKHS can also be written in this basis in this way. K, and then square root of lambda k, ek of x. So that's f in the RKHS, where this thing here, so this combination between the basis of L2 and lambda k, this is the what we call the features. That's the features of the kernel. And k are the eigenvalues of the kernel. So essentially, once you know this, doing, let's say, ridge regression on like non-parametric ridge regression, kernel ridge regression, is essentially doing linear regression on a Hilbert space. So for all purposes that we are going to see later, doing this, so kernel ridge regression is essentially equivalent to ridge with, you can think as ridge in infinite dimensions. Of course, you need to make sense of what it means, infinite dimensions, and the way to make sense is to have the minimal structure that you need to be able to write your predictor. Well, if you look at your predictor, the minimal thing that you need is a scalar product. So the natural structure is a Hilbert space. Okay. All of that, there is some caveats because, well, defining this thing requires more work. You need the reproducing property and so on. But I claim that A, B, and C can be equally studied with the methods that we're going to see next. I could give another example, which let's say is a neural network. So that's like a two-layer neural network. So we are not going to study this next, but you can also fit in this framework. So in the 3 minutes that is left, I just want to show you that all these examples, either for Bayesian inference or from ERM, they all going to fit this kind of a Gibbs-Boltzmann view of the world. So that's the last thing I'm going to say today. And then next time, we're going to introduce the methodology that we're going to use to study this Boltzmann-Gibbs distribution, actually to derive large deviation rates for this probability distribution. And the story is going to be exactly the same story as we had for the co-revised model. So under some assumptions, we're going to be able to derive large deviation potential. We're going to study the large deviation potential. And we're going to draw conclusions about the computational limitations for this type of problems. So all of these models, so both 1A, 1B, and 2A, 2B, and 2C are particular examples of the problem of studying. I'm going to introduce a probability distribution on the space of parameters. There's going to be some normalization. And then there's going to be a likelihood. This likelihood is going to depend on X only through the projection on some theta star, where this theta star is drawn from some kind of prior distribution, which I'm going to call phi. So this writing contains all the above problems. So it's quite obvious for the base optimal case, because I just need to take psi and phi to be equals to the prior and to the likelihood of the data generating process. But let's say for the ERM, so what these things correspond to. So for example, for the ERM, so psi of is going to be exponential of minus beta, the loss function. And phi of theta is going to be exponential of minus lambda r of theta. And so, as we said before, when beta goes to, oh, sorry, I forgot the beta here. Very important. When beta goes to infinity, so when you look at zero temperature, this measure is going to peak in the solutions which are the minimum of whatever is in the exponential. What is the minimum of whatever is in the exponential? Well, this is precisely this. Okay? So I claim if you understand the large deviation principle for this measure, here you understand the ERM. But if you understand the large deviation principle for this measure for the case where psi and phi, let's say, come from some Bayesian inference, you understand like your Bayesian inference problem. Let's say the phase retrieval, linear estimation, compressive sensing. All these problems, all this class of problems, which are defined through a likelihood of y given the projection of x in one direction, where x is drawn from some pseudo distribution, because this is not even normalized, but this doesn't matter, because I'm normalizing the overall measure. All these problems can be studied with the techniques that we're going to see next lecture. So our goal of next lecture is going to be to derive a large deviation principle for this class of problems, which you're going to call like, generalized linear estimation. And of course, you might ask like, well, what if I have more complicated loss functions? Let's say the square laws of a two-layer neural network. I claim these methods can still be used for these problems. It's just going to be much, much, much more complicated than what we're going to see next time. But you should keep this in mind that this offers a flexible tool to study a very large class of problems. So yeah, thank you for your attention and see you tomorrow.